guys, so today we're working on the Curtius rearrangement, and the major players in this reaction include activated carboxylic derivatives. Here we have acetyl chloride, and it will interact with nitrogen in the form of sodium azide to give us isocyanate. Now, it's important to note that isocyanate is unstable to hydrolysis, but because of this, in lab settings, it can be used as an building block to create things like amines, ureas, and carbamates. Now, but before we can form this, we have to start with our starting material, and we go through an intermediate that we call nitrene and then get to our isocyanate. If you look at our intermediate and our final product, it looks as if the nitrogen and the carbonyl have switched places. But let's take a closer look in our mechanism. First, the azide attacks our carbonyl, causing the electrons to swing to the oxygen, giving it a negative charge, and when the carbonyl reforms, chloride is kicked off, and here we're left with this, which is close to our intermediate, but not quite there. We have a positive and negative charge left on these nitrogens. Now, to make it happy, the electrons move to form a bond here, causing this electron to move to this nitrogen, giving us this molecule with a positive charge here. In order to get rid of it, the electrons in this bond move to this nitrogen, and the N2 is a leaving group, and we're left with our intermediate. Now, this is the most important step. This final nitrogen has an unfilled octet, and in order to be happy, the electrons from here move to form a double bond, but instead of disturbing the carbonyl, the R swings to connect to this nitrogen, giving us our isocyanate. Now, we'll draw this part together. We'll start with the oxygen. Since that hasn't changed, it remains double bonded to our carbon, and our carbon has a new double bond to this nitrogen and a single bond to our R group. And that's it, the Curtius rearrangement. Now, as they say, practice makes perfect. So here I have a practice problem for you to try on your own. Go ahead and do the mechanism, predict the product, and we'll come back to see the final answer. Over here, I have the Curtius rearrangement being used in a literature synthesis. Our starting material has a carboxylic acid, and in our reagents, we have a cross-coupling reagent that helps get the azide to our molecule and a TROC protecting group with the alcohol. Our final product is a protected amine, and we can tell that the Curtius rearrangement was used in this step because of the placement of our nitrogen.